Okay, welcome back, everybody. We have 6 more lectures in the class. So that's great. We're getting pretty close to finishing. So today I'm going to tell you a little bit more about Laplace transforms for ordinary differential equations with some kind of an external forcing. And Wednesday we're going to look at Laplace transforms for solving PDEs. And then after that, that leaves 4 lectures to talk about data methods, dimensionality reduction, and a little bit about numerical solutions to PDEs. So it's just kind of a teeny, teaser at the end about data stuff. Okay. So the last thing I told you last time was about the frequency response. So if we had something like a spring mass damper system, and we have an ordinary differential equation like x double dot plus 5x dot plus 4x equals some external forcing u. And this has units of acceleration or force. Then I have a transfer function, which essentially tells me in the Laplace domain, x bar, my Laplace transform solution divided by u bar, is equal to 1 divided by the characteristic polynomial. So that's s squared plus 5s plus 4, 1 over that. And this is called my transfer function, big G of s. Okay, this is just a recap of last time. So what I showed you last time is that you can look at the magnitude and the phase of this transfer function, and it tells you how this system is going to react to sinusoidal forcing at given frequencies. Okay, so we look at the magnitude and phase of this transfer function at I omega. So we plug in I omega in for our Laplace variable s. And we look at the magnitude or the phase. And that tells me the magnitude and the phase of the sinusoidal output in response to sinusoidal forcing. So I'll just show you a little Matlab script, a quick script that allows us to compute this. And I just want to convince you that this actually is, in fact, useful and what we think it is. Okay, so this is going to be pretty simple, a simple script. So I'm going to clear all, close all CLC. I'm going to make my transfer function, which is just a Laplace variable s. And from that Laplace variable s, I'm going to make my system, which is 1 divided by s squared plus 5s plus 4. My transfer function. I could call this G if I really wanted to. Okay, and I'm going to look at my Bode plot. Figure Bode of G. This is just my frequency response. And I get a plot like what we had before. So we see that at low frequencies, for really low frequency, x-axis is frequency, we have a constant amplitude sine wave output. So this is just constant at 0 phase, meaning it's exactly in phase with my forcing. And then as I force this thing faster and faster, the magnitude of my response gets smaller and smaller and smaller. And it becomes exactly out of phase, 180 degrees out of phase with my input. This magnitude is on a log scale in decibels. So like every... so this is on a logarithmic scale. So minus 80 dB is a really tiny number compared to minus 10 dB. Okay, so what I can do now is, what I'm going to do first is I'm just going to create a sine wave and run it through my system, see what it looks like. So my time is going to be a vector from 0.01 in increments of 0.01 to 100. And u is going to be sine of t. I'm just going to input a forcing at frequency 1. And y is going to be LSIM of my system G given u given t. Did I show you LSIM last time? Yeah? Okay, good. It's just a linear, it simulates a linear system with an input u for time t. And I'm going to plot t by y in black. Okay, I get my Bode plot, I get my sine wave. It looks super choppy. Maybe I messed up my dt. Probably did. Yeah, so it should be 0.1 in increments of 0.1 to 100. That looks better. Okay, so this is what the system actually does in response to a pure tone sine wave. And now what I'm going to do is I'm going to use the information from my Bode plot to see if I can predict what that sine wave is. So I told you that the magnitude and phase of g I omega is going to be useful. So we're going to see if we can actually reconstruct that using just the transfer function. Okay, so what was my omega? What was my frequency? Just 1. All right, 1. Okay, so my Laplace variable is going to be I times omega. And then I'm going to plug in, I'm going to get the magnitude. Okay, how do I do this? So now I'm going to say g of s is equal to, so I just redefined my Laplace variable s. So this is no longer an actual transfer function s, it's a number, I omega. And so what I'm going to do is I'm going to recompute this expression where s is I omega. And then I'm going to look at the magnitude, which is the absolute value of g of s, and my phase is going to be the angle of g of s. And I'm going to hold my plot on, and I'm going to plot time by my magnitude times a sine wave of frequency t plus phase in red. Okay, does this make sense what I'm doing here? I'm redefining my Laplace variable so it's just I. And I'm going to plug that into my transfer function. This is just me evaluating my transfer function at I, at s equals I. I'm taking the magnitude and the phase, and I'm constructing a sine wave with that magnitude and that phase, and t times omega. So maybe I should put times omega in here, because if I change omega, I want my frequency to change. So now when I plot that, I get this red dashed line. And we see that we perfectly get the magnitude and the phase. And look, the magnitude's not 1. It's 0.17 or something. And we're perfectly capturing the magnitude and the phase of the sinusoidal response just with 2 numbers from the transfer function, the magnitude and the phase of g evaluated at I omega. Does that make sense? Okay, so this is an extremely powerful tool. If I look at this transfer function, I can tell you what your system is going to do to sinusoidal input of any frequency. I can tell you exactly what its magnitude and phase of the sinusoidal response is going to be. Super useful. A lot of information on one graph. Okay, any questions about this? This is a really important thing in control systems and in mechanics and vibrations and materials if you want to know where your system might be sensitive to instability or resonances. Because if you see a sharp peak anywhere in this Bode diagram or this frequency response, that tells you that there's some input frequency where if I force my system, I get a lot of response out. I might even get an amplification in the response. And that could cause system fatigue. It could cause failure. So on an airplane wing, I would want to do the frequency response of the actual wing to different aerodynamic frequencies, low frequency turbulence, high frequency turbulence. And I want to make sure that it doesn't have any big resonant peaks that's going to cause the wing to be shaking or vibrating, because that'll essentially cause fatigue and eventually failure. Okay, so you do this on essentially all testing of materials where you think that you want to have a long life and there's going to be some vibrations involved. When I was a kid, I lived near a newspaper printing press. And apparently newspaper printing presses generate a tremendous amount of vibrations at a certain frequency. They just they'll shake the entire city block. So it's a printing press that's almost as large as a city block, and the whole thing's shaking. And they had to put the entire printing press on top of a cork platform to damp out a huge vibrational mode so that it didn't shake everyone within blocks of this printing press. So you can actively suppress different frequencies if you want, if you identify them in this frequency response. Okay, good. So we're going to be going back and forth to Matlab a little bit today. Okay, good. So this is the general idea. I have a physical system, an ordinary differential equation. I can write down a frequency transfer function in the frequency domain by taking the Laplace transform. Okay. So now what I want to talk to you a little bit about is the impulse response. So I've already alluded to this impulse response, which is essentially what would happen if I give my system an impulsive input. Okay, so the impulse response is essentially what I would get if I gave my input u a delta function. So this is if u of t equals a delta function of t. Now remind me, what are the properties of a delta function? Its integral is 1. Yeah. What does delta look like itself? Super duper sharp, like it's an infinitely tall and skinny, point like that. Right? It goes up to infinity, but it has infinitesimal width, so it has exactly area 1 under its curve. And if I integrate this, so if I run this through an integral, then at exactly time t equals 0, my system goes from 0 and it steps up to 1. It integrates up that unit area, and my integral becomes 1. Okay, so that's the property of my delta function. What's another property of my delta function? If I integrate some function f of t by delta t at dt from negative infinity to infinity, what do I know about this integral?
Just evaluated at 0. Value of f.
Okay, it's just my function f evaluated at the time where this delta function is non-zero. Because you could essentially say this is f times 0 everywhere except time equals 0. And then exactly at time equals 0, this thing integrates up to f of, so this is kind of like integral negative infinity to infinity of f of 0 times my delta t. Because delta t is 0 everywhere except for 0. And then this is f of 0 integral. And that just equals f of 0. So in general, if I have a function f of t, and I integrate it with a delta function t minus a, so I'm shifting this so that the delta occurs at some time a, then this is going to equal f of a. This is just a really useful property of the delta function. I'm just telling you this is going to help on the homework. And I realize I probably didn't mention this at all before. Okay? So we're going to be using this delta function impulse response, and we're going to start thinking about how our system responds to this delta function. So the really cool thing about a delta function is that even though it has infinite magnitude, it occurs in an infinitesimal window, and so it only adds a finite amount of energy to my system. It doesn't make my system blow up. It's just like taking my spring mass damper and hitting it with a hammer. It might happen very, very quickly. It's very high magnitude force, but it only adds a finite amount of energy to the system. Okay, so I'm going to draw some pictures, and then we're going to look at what the impulse response actually means. Okay, so this is t equals 0. This is my response x. Again, t equals 0. So my impulse response function is this super ridiculously sharp thing that goes up to infinity. I could get this a number of ways. I could take little rectangles and make them thinner and taller at the same time. I could take Gaussians and make the variance go to 0. That would all be fine. And what my system is going to do when I give it this kick, it's going to have some response. So it's not going to respond for time less than 0 because it didn't have any inputs. There's no initial conditions. And then at time equals 0, the system's going to do something. But eventually it's going to die out because it stops getting input. This will die out if it's stable, right? If all my eigenvalues are negative real part. Okay, so my impulse response is this response to a unit impulse in U. Now, a couple of other things. if we have an ODE, so for an ODE, we have a transfer function. So for every linear ODE, we can get its transfer function g of s. We just Laplace transform 1 divided by the characteristic polynomial. And so in the frequency domain, I say x bar equals g bar times u bar. This is my frequency domain expression for my solution. And if I give this thing a unit impulse, then this is the same as g bar times 1. So I'm using a fact here that the Laplace transform of a delta function is just 1. Okay, so if my u is a delta function, then this is just g of s times 1. And I'm going to call this x sub delta, because this is my impulse response. So now, if I want to find my solution, x sub delta of time, that's this thing here, my response, given a delta function, x sub delta is just my impulse response, that's just equal to the inverse Laplace transform of g of s. So what this means is that my impulse response, the response of my system in the time domain to an impulsive input, is exactly equal to the inverse Laplace transform of my transfer function. This is a pretty cool property. This is a very important relationship. They're like siblings or cousins. Okay, so this is super important. I'm going to box it. The impulse response is the inverse Laplace transform of the transfer function, and vice versa. Okay, so there's a really simple example we can use to kind of visualize what's happening with the with this impulse response. So let's say we have a simple linear ODE like x dot equals, x dot minus lambda x equals u of t. So this is just a simple linear first order ODE with forcing. And let's say that I make this u a delta function. So I'm going to look at the impulse response of this ODE. I'm going to kick this ODE with some delta function forcing. I'm going to see what it does. Okay, and we're going to assume 0 initial conditions. Usually when we do impulse responses, we're just looking at the 0 initial condition case. So let's integrate both sides. Okay, so if I integrate x dot, okay, and also we're thinking, are we going to integrate, like what are the bounds of integration? What are reasonable bounds of integration for this system? Where do we want to know its solution? T greater than or equal to 0, right? So we're assuming for t less than 0, nothing's happening because there's no input. We're assuming exactly at t equals 0, there's this delta function. And then for t greater than 0, the system is probably going to decay, back down to 0 because it's a stable system, maybe stable. Okay, so I'm going to just integrate both sides from minus epsilon to see what this delta function does right around time 0. So let's integrate x dot dt minus lambda times my integral from minus epsilon to epsilon of x of t dt equals my integral from minus epsilon to epsilon of delta of t dt. Okay, so each of these terms is super simple, and we can just evaluate it. So what's the integral of x dot with respect to t? Okay, so this is x evaluated at epsilon minus x evaluated at minus epsilon. Minus, okay, so x is basically 0 around this entire time. It's very, very small, and dt is also very, very small. So this is essentially like 2 epsilon times something very small, and we're going to take epsilon going to 0. So I can say that this is 0. I'm waving my hands, but you can convince yourself that this term is 0. And this integral of my delta function is really easy too. What's the integral of delta from minus epsilon to epsilon? 1. This equals 1. Okay, what is x evaluated at minus epsilon? 0, because my system had 0 initial condition for all negative time. So this is just saying that x at time epsilon is equal to 1. And I could take this, I'm making a very crude argument. This is basically equal to 1. And x of epsilon in the limit as epsilon goes to 0 plus, equals 1. So this becomes exactly true as epsilon goes to 0. What that means is that this delta function at time 0 essentially gives my system an initial condition of 1 at time 0. So this delta function is just like an initial condition response. With x of 0 equals 1. And what is the initial condition response of a stable linear system? Just e to the lambda t. It's just decay. E to the lambda t. I'm assuming lambda is negative. Okay, so essentially what this delta forcing does is it establishes at positive epsilon an initial condition for my system, and then the forcing goes away. It never comes back. It was just a sharp spike, and then it was 0. After it gave my system this initial condition, for all time after 0, it just looks like an initial condition response. Okay, so if you were a detective and you came and were investigating this system at time epsilon, you couldn't tell the difference between an impulse response and an initial condition response. Okay, questions about this? Yeah?
The second term is approximated by 0.
Sure. So we know that x is basically 0 for negative time. And we think x might be non-zero for 0 to positive epsilon. It's going to be close to 1. But the integral, so this integral from negative epsilon to epsilon of x of t is actually going to be about epsilon. It's going to be about 1, the integral of 1 dt from 0 to epsilon. Let me draw it. So if I zoom in from time 0 minus epsilon plus epsilon, we think our system is going to look like, this thing's decaying, but if I zoom into epsilon, it's decaying really, really slowly, so it might look like that. And so it starts off being 1. The area under this curve is about epsilon. It's about epsilon times the height 1. Maybe it's slightly less than epsilon. But I'm going to take the limit as epsilon goes to 0, and so that term's going to drop out. Yeah, so yeah, you're absolutely right. This is a little bit crude, but you can argue that this should be 0, and it won't affect x equaling 1 at time infinitesimally small. Okay, good question. Other questions about this impulse response? Yeah?
Solving this, sort of like we're going through in the homework, will it actually come out looking like an initial condition response? Is that what you're saying?
It's different for higher order systems. So I'm showing you this just to give you an intuitive feeling of, for simple systems, an impulse response looks like you just give it some initial condition. So we're kind of adding to an initial condition. What you would really do in the homework for the impulse response is you do it this way. You would take the Laplace transform of your system, you'd multiply it by 1, and then you would inverse Laplace transform your transfer function. And this inverse Laplace transform of your transfer function will look like something, let's say that my system was second order, like in the spring mass system. So this would be 1 divided by s squared plus 5s plus 4. And I could factor it into 2 terms. Those would each be exponential terms, and my impulse response would be the sum of 2 exponential terms. And the coefficients would be determined by the partial fractions. Yeah?
If you factor it in complex roots, how would you go about that?
So when you inverse Laplace transform this thing, you'll end up getting cosines and sines, maybe with a damping or a growth. You'll get something like e to the lambda t times cos omega t plus I sine omega t. And probably all of the imaginary stuff will cancel out. Okay. Okay, good questions. Other questions? Okay, so this is that was the cartoon. Now I'm going to show you another more useful cartoon. Did I tell you how to do the impulse response in MATLAB? Just the impulse command, give impulse of g. And MATLAB has clever ways of approximating this thing. Kind of interesting. You can actually find some of the source code and figure out how it's numerically doing these things, and it's pretty interesting. Okay, so the nice thing about the impulse response is that it gives us an intuition for how we solve these systems with convolution. Okay, so I'm showing you the impulse response because I just want you to be thinking about what little kicks to my system does. It like gives me some initial condition response. So we know that our system, we can solve systems of ODEs with forcing using convolution. So I think I just shouldn't have erased that. But if I had, x bar equals g bar u bar, and I want to find out what is my system x of t, well, that's equal to the inverse Laplace transform of g bar convolved with the inverse Laplace transform of u bar. What is the inverse Laplace transform of u bar? It's just u of t. It's my input. It's my input in time. Okay, so times u of t. Now, inverse Laplace transform of my transfer function is this really special thing called the impulse response. Inverse Laplace transform of g of s is this really special thing called the impulse response. Okay, it's a function in time. It's how my system rings after I kick it. And so this equals the integral from minus infinity to infinity of my function g of t minus tau, u of tau, d tau. That's just the definition of a convolution integral. If I wanted to, I could have written it like minus infinity to infinity of g of tau, u of t minus tau, d tau. You can prove pretty easily that you can do the t minus tau in either argument you want. It doesn't matter. I like this one because it's much more intuitive what we're doing. And if I knew that my forcing, if I assume 0 initial conditions and I assume that time started at 0, then I can get rid of this and just integrate from 0 to positive infinity if I want. Okay, so this is really useful. We find that our solution in time is given by the convolution of our impulse response with our input u. So in a real practical system, what I might do, if I wanted to know how my airplane wing is going to respond, so I told you that my airplane wing might respond to low frequencies and high frequencies and all kinds of frequencies of turbulence. But I'm not, in reality, going to just get one pure tone of turbulence. I'm going to get a whole, input u of t of turbulence. And so what I might do with my wing is I might hit it with a hammer, measure its response, and then take that response and convolve it with my turbulence input u. That's not sinusoidal. It's whatever I want it to be. Okay? Okay, so now I'm going to show you, I want to tell you kind of intuitively what convolution means because I've been dancing around it, but it's really, really important. This convolution integral, how many of you have read homework 5, or at least glanced through it? How many of you have looked at the last problem? Okay, so we're going to use this convolution integral to simulate how sounds sound in a different environment. So one thing you can do is you can take a recording of yourself talking in an acoustically isolated room. So it's just your flat audio of exactly how you sound. It's different than how you sound in your skull. If you listen to yourself played back on a tape recorder, you sound different. So you can take that sound, u of t, which is what you sound like saying something, and then you can take the impulse response of a sound in a concert hall or underwater, or in a long hallway, or in a pool. And this impulse response, what you could do is I could just put a microphone back where one of you is sitting. I could detonate a small explosion right here, blast a shotgun or something, and record what you hear in your microphone position. I excite a really big initial sound, and then you record it. and you take that signal and you convolve it with any other signal you want, and what you'll get is how that thing would sound as if it was being played here and listened to there. Okay, so you can simulate. These are actually extremely valuable. These are worth real money. You can take the most expensive seats in a concert hall, and you can carefully compute the impulse response in those most expensive seats in a concert hall, and you can sell it to record companies. And they do this. They make very expensive convolutions to simulate how it sounds in the London Philharmonic Symphony Hall. Okay? Yeah?
That assumes like no interference or objects that block the sound waves.
No. This is capturing all of the interference and all of the objects that are blocking the sound waves. So when this sound is bouncing through the room and bouncing off the tables, and that's the perfect sound because everything is just so, this is capturing all of that. And I'm being a little careless here because the acoustic equation in a three-dimensional symphony hall is actually a partial differential equation. But these ideas definitely generalize to solutions of partial differential equations. We'll talk about that a little bit later. Okay, so anyway, let's do another simple example of convolution. So our second simple example is the following. It's the exact same simple example. We're going to look at x dot plus lambda x equals u of t. But maybe x dot, let's say x dot equals, that's a little bit better, equals lambda x plus u of t. We're going to have 0 initial conditions, and I'm going to have a function u of t, which is just a square wave pulse. So I want to know what this input does to this system using convolution. Yeah?
Is there any constraint on this based on whether it's a first-order system, second-order system, nonlinear system, or...
So this entire theory applies to linear systems of ODEs and linear systems of PDEs. There are analogs for nonlinear systems, but it's complicated and it's messy, and I don't believe it. So, like there are some good generalizations. The only really trustworthy ones are extensions to nonlinear. To nonlinear impulse responses are called Volterra kernels. And this was actually largely developed in the aerodynamics community to deal with nonlinear vibrational problems, actually on wings. Go figure. So Volterra kernels are essentially more and more G's that capture higher and higher nonlinearities, and it's complicated. But this is the only mathematically satisfying extension that doesn't seem like make-believe math to me. Okay. So how many of you have seen the convolution integral illustrated in a movie? Good, you're about to. Okay, so we're going to write a script in Matlab that's essentially going to go through and compute the convolution integral as tau goes through the system, as t goes through the system. And we're going to figure out exactly what this input does and exactly what convolution means kind of intuitively. Okay, so we have our input. Maybe I'll just write down the math here. So the solution of this is x of t equals the integral from minus infinity to infinity of e to the lambda t minus tau, u of tau d tau. You could get this any number of ways. We derived this in 564 last quarter. Or you could take the Laplace transform, get the transfer function, inverse Laplace transform, and do the convolution by hand. That's the same thing. And this, of course, is going to be the integral from 0 to infinity because we're assuming that we have 0 initial conditions and that u is 0 before time t equals 0. So this is the solution. And we're going to start building up this solution by convolution. Solution by convolution. Okay, so we take our system u. And what we're essentially doing is we're saying that every value of u is like, let me think of how to say this. So when u is not 0, what I'm going to do is I'm going to consider this u as a continuous train of little teeny tiny impulse responses. I'm going to say that this is a little impulse response, and its neighbor is a little impulse response, and that's a little impulse response, and that's a little impulse response, and so on and so forth. So this is a train of infinitesimally small impulse responses, of infinitesimally small impulse responses. What is the magnitude of this impulse response? This little infinitesimal impulse response. What's the area under the curve? No, that's the area of an infinite impulse response. What I'm saying is that the area under this little curve, this doesn't go up to infinity. It goes up to u. So the area is equal to u of tau d tau. And d tau is tiny. So essentially what I'm doing is I'm taking and saying that this is like a delta function, but it's got, instead of area 1, it's got area u of tau d tau, which this is effectively infinitesimal. D tau is tiny. But if I add up enough of those d taus, I get a real area. Okay. And every single one of these little impulse responses gives me an initial condition response with this teeny tiny infinitesimal initial condition. And so what I can do is I can go at a number of key locations. I'm just going through all of these locations, and I'm looking at what the initial condition response would look like for that infinitesimal impulse, and I'm going to add them all up. So I'm going to draw this picture. So at early times, u is equal to 0, and so my system response is just 0. Here, at time where this step turns on, I have a teeny tiny little impulse response, and so I get a teeny tiny little exponential decay. And here at time, in the middle of my response, I have another little impulse response, and I get another little decay. And at the end of my impulse response, maybe right at this point here, my system is flat again, and so on and so forth. So for every little point in this input function u, I'm saying that it's creating these infinitesimal impulse responses. And what I'm going to do is I'm going to add all of these up. So at time 0, I have 0 response. At time 0.1, I have 0 response. And then when the step turns on, I actually start getting a little response. And those responses add up until something meaningful happens. So my output response, my state x, is going to look like 0. And then as the step starts, I'm going to start accumulating some outputs. And then once the step turns out, I'm not going to be accumulating anything. Everything else is just going to die out. And so I get my exponential decay. Okay, this was not a movie. This was me drawing on the board. So I promised you a movie. And essentially what we're going to do is we're going to exactly compute that convolution integral using this idea. So every little u of tau delta tau is going to give me, so I could call this a u of, tau 1 delta tau impulse response. So I'm going to break this up into finite rectangles. And the area, these are now not infinitesimal, they're just small. Okay, questions before I actually do this in Matlab? Maybe I should do it in Matlab and then take questions. Okay. Okay, good. Maybe I will just play the movie first, and then I'll write the code. Okay, so here's the movie. I'm taking my impulse response, and I'm running it through. Okay, let me walk you through this. So this is my function u, the input. This second panel here is essentially showing my impulse response, and it's being time shifted because when this step turns on, my impulse response starts at time 5, and so I want it to be windowed there. So it's moving along as these red dots move. And what I'm doing is I'm taking this impulse response at this location in time times u of t delta t, and I'm adding it to my solution. So my solution is just accumulating response every time my u is non-zero. So let me run this again. So this is my output. 0, 0, 0, 0. Now it starts accumulating because my u is on. And then once u turns off, it just decays forever. Okay, so this is kind of pictorially what the convolution is doing. I can give it other inputs. It doesn't have to be a square wave. It can be a sine wave. Let's say that this is from minus 1.1 to that. So now my input is a sine wave. Okay. And notice that the output is a sine wave, right? We know that the input and the output of a linear system is going to be a sine wave to an input sine wave. But the magnitude and the phase are slightly different. We can get those from the frequency response. Does anyone want to see how I actually went through and wrote this code? Yeah? Yes, good. Okay. I was afraid everyone was going to say no. Okay, so let's clear all, close all CLC. This will be the last thing I do today, I'm quite sure. Well, it's the last thing I do in this class today, hopefully. But there is more in the notes, and I am not going to cover them on Wednesday. So if you're interested, read them. They're 3 pages. It's essentially a summary of how this would generalize to systems of ODEs, like x dot equals a of x, a times x. And I have a picture showing how I see physical systems. And I think you'll find it useful. But it's not really anything I'm going to examine over. OK, good. So we clear all, close all CLC. I'm going to create an S that's a transfer function. And lambda equals 1. And what's my transfer function for x dot equals lambda x? 1 over s plus lambda. That's what I would get if I Laplace transformed, if I took 1 over the characteristic polynomial. So my system is 1 divided by s plus lambda. OK, now I have to create, did I close the window? I did. So I have to create, I'm just going to run this again. So I need to create a vector of time from 0 to 15 that includes my input u. And then I also need to create a vector from time 0 to 2t to 30 for my convolution. OK, so I'm going to make dt equals 0.1, t equals 15, and my time vector is in increments of dt up to t. U is going to start out as 0. And I want to make it a square wave where the middle third is the square wave. So u of n divided by 3 to 2n divided by 3 is equal to 1. Okay, middle third square wave. And then I need to do something. I need to get my y impulse response. My WIMP and my TIMP are equal to the impulse of my system in time. Okay? Impuzzle. Okay, we don't want to impuzzle. We want to impulse. Good. And then the last thing is I need to create my solution vector, which is twice as long as my u vector. Okay, so my solution vector t solution is dt in increments of dt up to 2 big T's. X solution starts out being 0 times t solution, just 0 everywhere, and I'm going to keep adding to it. Okay, so now we need a for loop, right? Any questions so far? This is just a setup. Okay, so for k equals 1 to the length of my input u, My first subplot, 3, 1, my first subplot, I'm just going to plot the control signal u, so I have it up. So plot t by u by in black. And I'm going to hold on, and I'm going to plot the current time that I'm on in a red circle. Okay, so I'm plotting the whole signal u in black, and then I'm going to plot the particular time that I'm on, the kth time, as a red circle. So let's say I just ended here. Test conv2. Okay, so this thing basically just went through for k equals 1 to 150, and it just went through and plotted a red circle. You should probably say draw now and pause 0.05 so that it actually shows something. Okay, that's my first thing that I just did. Good. Now in my second subplot 3 by 1 by 2, I'm going to plot my impulse response, but I'm going to keep shifting my impulse response in time. Right? So I'm going to plot t imp plus t of k. I'm shifting by t of k. This is like my tau. Okay? I'm shifting by t of k. If I was really clever, I probably would have named one of these variables tau, but I think I would get confused. So one of these variables is tau. The other one's t. And I'm going to plot this in k. Okay, good. And then the last thing I need to do in my last subplot, I need to actually add up this impulse response to my solution. So now x solution from k to k minus 1 plus length of t. Okay, so my solution is this really long, twice the length of 2 vector. And every k, I'm stepping forward, and I'm adding up my impulse response to k up to the length of t. This is just a way of keeping track of the indices. So that's going to equal what it originally equaled, plus my impulse response, which is dt times u of k times my y impulse response. And I'm transposing it because it's a column vector and the other one's a row vector. Okay, this is hard to read. Maybe I will make it like that. So my solution vector at the current shifted values is equal to my old solution vector plus this new dt impulse response, dt times u of k times my impulse response. I think that's actually it. So now I get to plot it. Subplot 3 by 1 by 3, plot t solution by x solution in black. And it's nice to give myself some axes so that it keeps looking nice. Okay, anything else? Nope, I think this is good. No, that didn't work. I forgot to put the, oh, I'm just plotting time. Okay, let's plot my y imp. Good, thank you. Now the system turns on, starts accumulating. System turns off and just keeps decaying. Okay, questions about how we wrote this or what this impulse response means? Yeah.
You're saying like you have the t and the tau, but you didn't call anything tau. How does that? Can you like repeat how that showed up in there?
Yeah, I mean, I'm essentially taking this equation, and I'm literally just taking this impulse response shifted by tau. So t of k is my tau. I should have just called t of k tau. And then I'm just taking this and I'm shifting it to the right by tau, and I'm multiplying it by the magnitude of that impulse is u of tau delta tau. U of k dt in this example. And I can give any U I want. That's why the convolution is so powerful. That's why the impulse response is so powerful. Okay, next time we'll talk about PDEs. We're done with ODEs for now. Thank you.